Okay, this is the beginning of some videos on section 17.1 and 17.2. We've already done 17.3. I want to do that first. I'd like to do titrations first, and now we're going to look at the common ion effect. Now, the common ion effect is something that we saw when we looked at solubility equilibria. So if I have a solid, we'll call this some kind of salt, and it dissociates into its ions. If I were to add, let's say, sodium carbonate to this would shift the equilibrium in this direction, and the salt would become less soluble. And this common ion effect we saw with solubility equilibria. We can also have a similar type of shifting of equilibria when it comes to acids and bases. And this could actually help us in situations where we're adding extra acid or extra base to a basic or acidic equilibrium in helping to create what's called a buffer solution. All right, so the way that we're just going to start real simply, we're going to look at three solutions. The first one is just sodium acetate dissolved in water. The second one is just acetic acid dissolved in water. And the third will be the sodium acetate and the acetic acid mixed together. Okay? So basically, what's going to happen is I'm going to move down here. I've got acetic acid, and I'm dissociating that into this. It's hydrogen ion and the acetate ion. There's my equilibrium. Now, what I'm doing up here is just dissolving sodium acetate into sodium. Remember, these are naps, so they just completely dissolve. An acetate ion. So when I combine these two, I've got a little bit of this, a little bit of this, and I've added some of this. So I'm going to add extra acetate ion to generate the common ion effect. So let's start with how many moles of sodium acetate I have, because I'm going to create this solution. So I want to know how many moles of this I have. So I take 16.4 grams of this, and the molar mass is 82.03. 4 is 1 mole of sodium acetate, and that equals 0.200 mole sodium acetate. Now, sodium acetate is classified as a strong electrolyte because that's a nap, right? So it's going to completely dissociate into the two ions. If I have 1 mole of this, I'm going to get 1 mole of that and 1 mole of that. So the sodium ion concentration, if I have 0.2 mole of this, I'm going to get 0.2 mole of that and 0.2 mole of that. So each of these, that's the concentration. So there's my solution. I have 1 liter of that. Okay, so now let's make up my acetic acid solution. Now, my acetic acid solution, I've got acetic acid is classified as a weak acid, and so it's a weak electrolyte. Now, the Ka expression is really simple. I'm going to go up here, products over reactants. C2H3O2 minus divided by HC2H3O2. Okay, now, if I were going back to the last test, I want to calculate how much of these species I have at equilibrium and find the pH, and that is my initial solution. So because I only have acetic acid, and that's all, this is not the place to use the Henderson-Hasselbalch equation, right? This is just an ice table because all I have is 1 weak acid. So that means that Ka, now I'm going to go through this pretty quick. I'm not making an ice table here because by now you should be able to do this quickly. This is equal to x squared divided by 0.200. I can get rid of that because my Ka is very low. It's 10 to the minus 5. And so 1.8 times 10 to the minus 5. So x is equal to 1.9 times 10 to the minus 3 molar. And that is the hydrogen ion concentration and my acetate ion, C2H3O2 ion concentration. All of those are equal to this. So if I want to find my pH, I just take the negative log of 1.9 times 10 to the minus 3 molar, and that is equal to 2.72. Okay, now let's put these two solutions together and see what happens to our pH. Okay, we know what the pH is of a solution of acetic acid by itself. What do you think is going to happen when I add acetate to this equilibrium? I'm going to add some of the sodium acetate here. It should shift the equilibrium in this direction, cause this concentration to go down, so my pH should go up. Let's see if that is the case, if that is what actually happens. Okay. All right. So here are my two solutions. I'm going to mix them together. And when I mix them together, I'm going to create a rice table. And this is still the equilibrium I'm dealing with. It's just that I added sodium acetate here. Now notice that I started out with 0.2 and 0.2. Why is it now 0.1 and 0.1? It's because I added 500 of one and 500 of the other. I basically went and diluted it with the other solution. So my total volume now is 1,000. Take 500, mix them together, and I get, so now I've got 0.1 and 0.1. So that is an important step to remember, that I am actually cutting the concentration of each of these in half because I'm doubling my volume. This is going to be minus x as usual, plus x, and plus x. Remember, this initial concentration came from the sodium acetate in the last solution that I made. This is going to be 0.1 minus x. This is going to be x, and this is going to be 0.1 plus x. But these x's can go away, so that means this can be 0.10, this can be 0.10. And so what I do is I plug this into the equation, and I'm going to get that Ka is equal to the concentration of hydrogen times 0.10 molar divided by 0.10, which is equal to 1.8 times 10 to the minus 5. So the concentration of hydrogen ion is 1.8 times 10 to the minus 5. Notice that those cancel. And it's interesting here, the concentration of my hydrogen ion is equal to my Ka here, because these are equal, and we're going to see that in a minute why that is so. So if I take the negative log of 1.8 times 10 to the minus 5, I get 4.74, which represents also the pKa. Because if I take the negative log of this side and I get this, it should equal the negative log of this side, which is this. So the pH and pKa are the same at this point. Now, the hydrogen ion concentration for solution 2 we calculated as 1.9 times 10 to the minus 3. That was the calculation we did on the previous page. The calculation for the hydrogen ion here is 1.8 times 10 to the minus 5. Look what's happened. The concentration of hydrogen ion has gone down when we added the common ion. So when I added sodium acetate, I added this here, and that's going to cause my equilibrium to shift in this direction. So the concentration of this goes down and the pH goes up, or the concentration oh, you can see here, of the hydronium ion is going to go down because I'm pushing it this direction. So that is the common ion effect. So let's look at another system and how, under the same circumstances. All right, so this time I've got a different reaction going on. I've got hydrogen fluoride in equilibrium with H plus and F minus, okay? And what I'm going to do is I'm going to add a few drops of HCl. So HCl dissociates into H plus Cl minus, so I'm adding H plus, which should shift the equilibrium in this direction. So the value of this is right here is initially going to go up, right? Because I'm adding it. But then the value of F minus here is going to go down. So H plus goes up with the addition of that, and that pushes the equilibrium this way, and this therefore goes down. This can happen with bases as well. So let's look at the actual problem with a base. So actually, you know what I think I'm going to do? I think I'm going to stop there, and I'm going to make a separate video on the base.